Oh, Gabriel. It's got movies.
Oh. Not actually a movie, it's a simulation.
So in the second talk of the morning, we have Grant Light from Leeds, and he'll be talking about kinky stochastics or something close to this.
Something else, yeah. I suppose I hit the title, didn't I? There it was. Okay, so I'm going to talk about one particular stochastic PDE in actually one space dimension that, as some of you know, I've been playing with for years now with various people, and there's still plenty to do, and since I don't have much time, it's probably going to take me many more years. So the PDE looks like this, referring back to some of the things we've heard. So I've got an object phi, which is a function of time. The t doesn't mean a derivative, it's a label. It's a function of space, a very long subset of the real line usually. And of course, since it's stochastic, you might also give a label for the realization, although people don't usually, and I don't either. Okay, and I like the notation for SPDEs like that, where you just put a d to the left of phi of your field, and on the right hand side you've got two things, like in stochastic ordinary differential equations, one proportional to dt and something else which is the noisy bit. So I think on the slide I wrote it like that. Good. Okay, so the same thing. You can probably tell from what's on this slide and what's not on this slide that I'm a Class A person, a disciple of Walsh, more than a Class B person. But really, I like this idea. That's right, isn't it? A was Walsh and B was, yeah, okay. That I'm always thinking of what is done, or what I do at least, to discretize the equation, and it has to be discretized in space and in time. I'm just using what you might call the garden variety finite differences here. Simple discretization of the spatial operator up the top. And since it's additive noise, there's no great problem with adding independent noise at each site. Okay, so what's on the next slide? Well, I'll carry on talking about the equation for a minute. So there are various ways of thinking about this equation, obviously, and the first one that occurs, at least to a physicist, is in terms of a potential, so the on-site potential, if you like. So you write the what was here. One of the things that was here was phi minus phi cubed. Okay, so that's minus the derivative of a capital V, a function capital V, that looks like that, and hence the name given by some people to this equation, which is a phi-4 equation, okay, because there's a 4 there. Other people call it, I always forget which way it is, Alan Kahn, I think, because the point is it's got kinks. I'll carry on this slide for a minute. So a slightly more sophisticated way of thinking about it is, instead of defining an object V, which really works on phi at a point, define an object, an energy, type of energy object that's an integral. So you integrate over your whole domain. So you take a configuration, perform this integration, and you get one number, a real number, which is like an energy. Okay, so then you can write the SPDE in this idea, in this way, so you can start thinking of it in some sense as analogous to an Ornstein-Uhlenbeck process, that there's some stationary density and the noise is bouncing you around that. And in fact, in some ways that's the best way of thinking about it, I think. Okay, so just show you again what actually happens. So this is just a relatively small spatial domain. Okay, so x is going along here, my phi is up or down, and because of this, phi likes to be close to -1 or +1. Okay, but you've also got second spatial derivative of phi, which is keeping the configuration at any one time a continuous function of x, and because you start off with initial conditions of a certain type, or because you've run the process for long enough, you're not going to find a uniform field in the sense that it's everywhere close to either -1 or +1. You're going to see every now and then a kink, which is an interpolation from close to -1 to close to +1, or an anti-kink, which is the reverse. Okay, so that's really the point of all of this. This is what. I'm sorry. Oh, so this one is just 0, and the horizontal axis is space. Space. So this is one configuration. So you've frozen time, and you're showing the configuration at one time as a function of x. Okay, so phi is going up here, x is going along here. When I click on and run the simulation again, you see lots of configurations. So time is moving as we watch. Okay. So the start of the understanding of all of this is if you've got a 0 in here, you've got actually an ordinary differential equation in, well, sorry, 0 in here, and you set the time derivative to 0, you've got an ordinary differential equation in x, and you can solve it with conditions -1 at -infinity and +1 at +infinity, and the solution is a tanh function. Okay, so roughly speaking, this shape is a tanh function, like that. And if you take the other way around, take +1 at -infinity, -1 at +infinity, you get an anti-kink, which is just -tanh. Okay. Now remember, on the previous slide I said, if I give you a configuration, you can do an integral and get an energy. Okay, so if I give you that tanh configuration, do the integral, get the energy. What's the energy? Well, it's the square root of 8 over 9 in these units. Okay, so the idea is attractive, thinking of these kinks as particles with a certain mass, which is given by that energy. Okay, so what happens in the long run? I can show you in a few seconds a simulation. I mean, this is actually running as we speak. It's not a movie, but it's just a relatively small spatial domain, and I chose it to have a couple of kinks and a couple of anti-kinks so you can see something. Okay, but what Salman Habib and I actually did was try to do proper statistics on this. So use the biggest domain we can get, run it for as long as we can, and see what's actually happening in the long run. Okay, so what is happening in the long run? Well, these kinks and anti-kinks, because of the noise, tend to follow Brownian paths. They move around. If two of them ever find each other, so if this one wanders too close to this one, they kill each other, they annihilate. This part of the configuration flips over to the top. You've got one fewer kink and one fewer anti-kink. Okay. On the other hand, in the sloshing around here, in the bottom one well of the potential, you've got noise, and every now and then that sloshing around is strong enough to throw some part of this configuration over the hill and create a new kink and a new anti-kink. Okay, so if you wait long enough, you'll see a dynamic balance between nucleation of new pairs and annihilation of existing pairs. Okay, so intuitively that's what happens in the long run. A little bit more rigorously, you can write down the stationary density of this system. Okay, so rather than worrying about the continuous limit, we can explicitly do this in the discretized system. In fact, even discretized with the choice of Laplacian that we use. So think about using n points, capital N, which is a large number, discretize this system. I mean, a very large number in practice, 10 to the 6, 10 to the 7, or whatever you think your computer can handle if it's not running too slowly. And the stationary density is just this. Okay, so it's something, as you'll see, along the lines of what Andrew Stewart and Jonathan Mattingly have mentioned in a different context, although the connection is very clear, and I'll mention that shortly. Okay, so you've got this function h, which is just given by that. Okay, so the stationary density, large but finite dimensional space, is explicitly given by that. It's nicely ergodic and so on. Okay, so in principle we can calculate anything we want. We can try to calculate the density of kinks, the mean squared value of phi at a point, correlation functions, whatever you want. In principle, it's all there because we know what the stationary density is. So long time quantities can be measured. You can compare it with numerics, see how good your algorithm is, see what your convergence in space and time is like, and actually study these coherent structures, these kinks, which are fun to study, but with some certainty that you know what you're doing, that you've got some convergence of some type. Okay, however, what's the but? There's z here, so partition function, just the normalization constant in front of that stationary density. If you want to actually get a number out of this, you know, what is the mean square or something, you're going to need to know what that number actually is. Okay, so why is that a problem? Well, you have to evaluate z by just integrating over this thing, over all the variables. And you can't immediately do that integral because of this part here, which comes from the coupling, the Laplacian, the spatial operator in the SPDE. This couples neighboring sites, obviously. Okay, so here's t written in general, this function of two variables t. Okay, and you want to perform this integral n times, but they're all coupled to each other, or neighboring sites are coupled to each other. Okay, now it turns out there's a clever method that people like these guys in the 70s came up with to actually perform that integral. Okay, so the argument runs like this. Suppose we can solve a Fredholm equation like that. Okay, so suppose we can find functions psi and eigenvalues t such that this is the case. Okay, then you can write this function of two variables as an expansion in those functions, and the integral just collapses and it becomes sum over little n of all the tn's to the power big N. Okay, now big N, remember, is enormous, 10 to the 6th, whatever you want. Okay, so obviously, supposing there's a largest eigenvalue, that's the one that matters. Okay, so you can get the z in the limit as n tends to infinity, which is the limit tending to the continuum SPDE that we're interested in. You can actually get the z. Okay, so remember I said if. Okay, if we can find these functions. Okay, now it turns out that you can find those functions in the limit that you're interested in, large n, small delta x, and they come from solving every physicist's favorite equation, the Schrodinger equation. Okay, so this v is the same v that you've seen a few times, minus the derivative of that, double well potential. Okay, so solve the Schrodinger equation, find the eigenfunctions and the eigenvalues. Okay, you can imagine that the lowest one, when the temperature is small, which means beta is large, is a function that's localized at the bottom of the wells, and you have this tunneling phenomenon, again, if you know about these types of things, which means that the second lowest eigenvalue is only slightly separated from the lowest eigenvalue. Okay, but so this is really useful because it gives you a way to get quantities as accurately as you like that are to do with a nonlinear spatially extended system, a stochastic PDE, and what happens when you solve it for a long time. Okay, so on the one hand, you've got these numerical experiments when you just solve the SPDE on the largest domain you can get, largest computer you can get, try to measure quantities like the mean density of kinks, number of kinks per unit length, that sort of thing. On the other hand, you can write a little program, it's still writing a program, to solve the Schrodinger equation, get these eigenvalues, and you get the same answer. The same answer in what sense? So, for example, suppose I've got my long system, my stochastic PDE, I choose one point, one point in space, and I look at the distribution, plot a histogram of values of phi at that point. Okay, so remember, roughly speaking, phi likes to be close to -1 or close to +1. Okay. Now the density of phi at a point is not just e to the minus something times v, the on-site potential, it's e to the minus something else because you've got the coupling between sites, because you've got the spatial operator as well. Okay, so what is it? What is the stationary density at a point? Well, it's the square of the lowest eigenfunction of that Schrodinger equation. Okay, it's really nice, I think. Okay, so you can generate this eigenfunction and square it and plot it. That takes maybe a few seconds, Maple or something. And you could run your SPDE, takes several days on a supercomputer, and do what I just did, plot the histogram and see that it works. Okay, with some finite delta x, in this case delta x equals 0.2 that you can do. Okay. What else do I mean? Correlation function. Okay, so think of your reference point in x, and as a function of distance from that reference point, measure the mean of the product of phi at those 2 points. Okay, so the correlation function is the mean of phi at some arbitrary chosen 0 times phi at x at the same time, okay, as a function of x. So it's something that decreases as a function of x. The mean square at the same point when x equals 0 should be roughly close to 1. Turns out to be less than 1, 0.87 in this case. And it decreases, and in fact you can show that it's exactly given by this. It's the sum of exponentials. Okay, the sum of exponentials, each exponent is a difference of eigenvalues, and you've even got the constants as well, just by an integral over the eigenfunctions. Okay, as x gets larger, so the distance between your 2 points, measuring the mean of the product, gets larger, that tells you something very important. Basically, it tells you the density of kinks, okay? Because the mean of the product in the long run depends on whether there's a kink in between the 2 points that you're measuring the product of, okay? So, more specifically, there's this idea of a length lambda, which is actually the smallest exponent, which is giving you the density of kinks. So, the last graph, again, following on from what Gabriel said, it's a straight line, but if you've had to do this yourself, it's the most amazing graph in the world. So each one of these dots is numerous hours of computer time solving an SPDE. The solid line is got from the eigenvalues and eigenfunctions of the Schrodinger equation, which takes a couple of minutes, and the dotted line is actually a WKB approximation to those eigenfunctions and eigenvalues. Okay, so number of kinks per unit length. This is a log scale, so the reason why, although it looks like the simulations are really easy because I showed you one on the screen and only took a few seconds, the reason why to do this properly and get the statistics right is incredibly expensive in terms of computer time is that every time you increase beta by a unit of 1 or something, it gets so much harder because you've got exponentially fewer kinks per unit length. It takes longer to reach equilibrium. So you need to run your computer for longer and you need a bigger computer to do it. Okay. That's right, you're supposed to say wow now, yeah. So I mentioned the connection with the work of people like Andrew Stewart. Not so long ago. Okay, so it's quite interesting that from their point of view, the SPDE is something that you invent to study something that you're actually interested in. Okay, but it occurs to me that I can do this the other way around. I'm actually interested in the SPDE, so I might be able to use an SDE or a bridge diffusion or something like that to get at something that I'm interested in. Okay, so well, first of all, the argument. So you've got an invariant measure on the space of continuous paths defined by the stationary density of that SPDE. Okay. On the other hand, you can write a diffusion process, a bridge diffusion process, if you want something special at the boundaries, which also defines the density on the space of continuous paths. Okay. And all you have to do is find a drift here in the SDE that corresponds to the function f here in the SPDE, and they're related in that way. Okay, so it's extremely attractive in a practical way. For example, you can get around one of the most annoying aspects of solving the SPDE and trying to study the stationary distribution, which is letting it run until it reaches equilibrium. Okay, so if you can solve an SDE in this, what to me is a fictitious time variable, so you produce a path that looks like what you were asking me a while ago. You see this thing like that, and is the x-axis, is it space or time? Okay, so in my case it's always been space, but wouldn't it be nice to solve something in time that gives you the right shape? Okay, samples from the right distribution. And apparently you can do it if you choose the right A. I haven't tried it yet, but if I get some more time or a postdoc or something to do it for me, then I certainly will. Okay. Right, okay, so back to the dynamics. I sort of said off the cuff, and you can convince yourself of it quite easily, at least by eye, that if you look at the position of an isolated kink, it diffuses. Okay. More specifically, you can do analysis of a type like this. So take the field phi as a function of x in some region where you know there's just one kink, and decompose it in this way. So this is a tanh function, and this is everything else. Okay, so it's not exactly a tanh, obviously. It's quite noisy. Even in here, it's a bit noisy. But if you do that and you use this quantity kt over ek, so kt is the amplitude that goes in here, and ek was the energy of one kink, roughly 1 in these units, okay, then you can explicitly get the diffusion coefficient, okay, half the mean squared displacement divided by time, as time tends to infinity, okay. So once again, you've got this nice interpretation that a kink is like a particle with a certain mass, and that certain mass is the energy that you can calculate by doing that integral. Okay, that's one part of the puzzle, or the picture of the dynamics. So now if I look at this is a space-time diagram that comes from a large scale simulation of the SPDE. So I've got space along here and time going up there, and I've thrown out all the information except for where the kinks and the anti-kinks are. Okay, so each space-time point corresponds to the position of a kink and an anti-kink. I think I can actually make that bigger. Yes, okay. So some kinks are lucky, time's going upwards. Some kinks are lucky and live for long times because they never hit anything else. Okay. Others are not so lucky. Let's see, here's one that's living for a long time, and then it hits something and dies. Okay. Now kinks and anti-kinks are born in pairs because new kinks and anti-kinks are created by part of the configuration being thrown over the hill, so they have to be created in pairs. They have to die in pairs. So what you're seeing that looks like kind of rubbish on the screen, little dots here, are actually little loops. So kink and anti-kink are born quite close together, diffuse, and then die quite soon. Okay, so these are all little loops. This is a slightly bigger loop. And the unusual long-lived kinks happen when something like this happens. So a kink and anti-kink are born together, they're wandering around, they almost hit each other, but they didn't quite. In fact, one of them hit something else. Okay, and then the partner of this guy ends up in its own region with no kinks around and having a long and happy life. Okay, so how am I doing? Fine. Okay, so I can study a different type of dynamics, which is of interest to a different type of people, mostly chemists, which just says, imagine dynamics of that type. So you've got the real line, you've got point particles on the real line, they diffuse independently. If two of them ever meet, they both die, and new particles are created at random positions in random places. Okay, so there are actually two variants of this. One is where particles are created one at a time with a certain rate, and the other one is where they're created in pairs, relevant to the kink case, with a certain rate and a certain separation at the initial time. So again, this is a space-time diagram of the simpler model, this model. So space along here, time going upwards, you see a little nucleation event, you see some annihilation events, And the same thing happens. Let this run for long enough, you get a stationary density, meaning number of particles per unit length. Okay, I'm thinking about kinks, but for the moment I've taken a step back and just thought about point diffusing particles. Okay, so what is the number of particles, or the mean number of particles per unit length as a function of time? Okay, this is a type of thing that chemists thought about, and the first thing that occurs to a chemist is that let's look at the case where particles are created one at a time. So you've just got this Q, that's the rate of creation of new particles, and the first thing you would say is that a reaction involves two particles, therefore the rate of reaction is proportional to rho squared with some constant. Okay, if you believe that's true, you can solve that ODE, then you'd find that the steady state density is proportional to the square root of Q, the mean number of particles per unit length, if you wait long enough. Okay, and if you could have a system with a certain number of particles in it and turn off the nucleation, just watch the particles find each other slowly and kill each other, then the density should decrease as a function of time, like 1/t. Okay, but neither of those things are true. If you actually do that, if you actually solve that model, it's very easy to do. In fact, I always forget where I'm supposed to click. Let's see if this works. Okay, yes, so I can actually solve the simple model. This is just, let's see if it comes up. Good. Okay, point particles. So I start off with some particles. Time is going upwards. Space is along here. Two particles ever meet, they both die. Occasionally new particles are created. If I run this for a very long time, I'll get a well-defined steady state number of particles. Okay. And if I turned off the nucleation at some time, I'd still have the annihilation, but there wouldn't be any new particles being created. The number of particles would decrease. Okay, so some people tried to fix this by calling it some type of anomalous diffusion and changing the exponent here from 2 to 3, which works. It solves actually some of these problems, but it doesn't explain the whole dynamics. So what I want to tell you is that you can actually make some exact statements about this slightly simplified system, and the rate of change of this quantity rho, ddt of rho, looks like this. So there's a rho squared indeed, but you have to do this integral to evaluate what the coefficient might be. Okay, so define a different type of correlation function, a point correlation function if you like. So choose a reference particle and measure the density of particles at a distance y away from that reference particle. Okay, it's a function of y and t now. Okay, and then you can say the rate of reaction is given by this. Okay, if I know how many particles are a certain distance away, and I know the quantity k, which is which is derived from the probability that two particles at a distance y away have met and reacted before time t, before time delta t. Okay, so k looks like that. Okay, so if this is going to be a sensible ordinary differential equation, then we need this thing to be a constant. Okay, now we don't know what g is yet, but we can do a Taylor expansion because we know what s is. Okay, so this is the probability that two particles diffusing with diffusivity d, distance y apart, meet before time delta t. Okay, so we can expand g in the Taylor series about y equals 0. Okay, and we immediately see something interesting, which is this square root delta t here. Okay, now remember I have to divide by delta t and get a limit as delta t goes to 0. Okay, so the conclusion is that g0t is 0. Okay, so this is, if you remember what the definition was, the density of particles at a distance y away from our test particle. Okay, so it says the density of particles next to the particle that you know is there is actually tends to 0. Okay, which when you think about it is logical, because if two particles ever meet, they both die. Okay, so the probability of finding a particle close to a particle that you know is there tends to 0 because chances are they've already met each other. Sorry about the hand wavy explanation, but anyway, so you can show that that is true. G0t is 0 for all t, except perhaps t equals 0 if you choose the wrong initial conditions. And then that the rate of change of the overall density of particles is given by that. Okay, so you take this quantity, I put 0 plus because g doesn't really have a meaning for negative y unless you just define it to be a symmetric function. Okay, one more thing, you can actually get the exact mean density of particles by an interesting trick. Define another quantity, which is take some region of width x of your infinite domain with particles in it, and write down rxt being the probability that the number of particles in that region is even. Okay, not 1 or 2 or 3, but even or odd, of course, is the other possibility. And it turns out that that satisfies a linear partial differential equation, which you can solve, and it's related to the density by that relationship. Okay, so you can solve for r and get rho as a function of time. So in some sense, you've got exactly everything you wanted from that model. Okay. And it might not be obvious, but the reason that works is just Glauber dynamics. It's the same trick as one-dimensional Ising model. Okay, so this was a road that I went down, or that we went down, because it was supposed to shed light on the SPDE and kink dynamics in the SPDE. Okay, so back to the SPDE with this in mind. This is now, okay, this is still the simple model, the reaction diffusion model, but this is actually solving the SPDE. Okay, so I start with initial conditions where there are lots of kinks and anti-kinks, and I watch them die. So this is really, you're supposed to say again, wow, this is just like the simple model, but now it's the SPDE. So I just plot as a function of time the position of each kink and each anti-kink. Okay, so there were lots at the beginning, but most of them died quite quickly. As time goes on, you see annihilation events. Now, in the time that I'm going to show this, you won't see any nucleation events, but in the long run, there will be a balance. Okay, balance at quite a low density of kinks and anti-kinks, exponentially decreasing with this quantity beta. Okay, so the density of kinks is proportional to e to the minus beta ek. We know that exactly in principle because it's the difference between the two lowest eigenvalues of that Schrodinger equation. The equation gives you the correlation length, which gives you exactly the density of kinks. Okay. Nucleation events occur at random space-time points with a rate proportional to that. Okay, now that's a hard thing to calculate. However, it's intuitively clear that that has to be the right result because a nucleation event creates a kink and an anti-kink. Each of them has a certain energy, so you've got the 2 ek there. Okay, and by thinking about how this all works, you can get the mean lifetime of a kink. Okay, mean lifetime of a kink obeys that relationship. The overall density is the nucleation rate multiplied by the lifetime. Okay, now that's interesting because if you think about this dynamics, the density of lifetimes of a kink is not a simple function. There are lots of kinks that have short lifetimes. There are a few kinks that have very long lifetimes. But by some amazing coincidence, we know the mean of that distribution. Okay. Yeah, there's one more thing, which is in the simple model, which is supposed to explain or shed light on kink dynamics, we've got the nucleation rate, we've got the diffusivity, and we've also got this separation at the instant of birth. Okay, so what might that be? Okay, so a different type of numerical experiment you can do to try to figure out, understand a little bit more about the nucleation process, and in particular, what's the characteristic width of a region that's thrown over that barrier, is start with a short chain. So explicitly I've shown each dot in a numerical simulation, each site as a dot, okay, And let's see what this does. Yeah, okay, so start them all at -1, periodic boundaries, and see how long it takes for them all to get to +1, or for them all to be positive. Okay, so if I've only got 1 or 2 of these little blue balls, 1 or 2 sites, a very short domain, you'll wait around for a while, and then suddenly they'll all jump over together. Okay, if I've got a very long domain, then some subset will move over, and then perhaps yes, perhaps not, depending on the diffusion of the boundaries. The boundaries will either expand and the whole domain will end up on top, or they'll collapse back down again and the whole domain will end up down the bottom. Okay, so there's a kind of transition as a function of this length, the length of this domain, in the characteristics of the time that it takes to do this complete passage. So start with all your configuration in -1 and see how long it takes to get all your configuration greater than 0. Okay, so if you do that as a function of L, the length of the domain, so initially it goes up exponentially. It's just how much energy does it take to push a certain amount of the domain over the hill. Okay, but then it flattens off because you've got a different type of behavior. You only throw a certain part of the domain over, and then diffusion widens that domain eventually to take up the whole, widens that nucleated subset of the domain to take up the whole domain. So the complete passage time, we called it, as a function of L, goes up and then flattens off. Okay, so where this knee is tells you what the characteristic width, that parameter b, should be. So it's between 5 and 10. I'm nearly done. I'm nearly out of time. Good. Okay, so a few questions, and I suppose I didn't talk about motivation very much. Maybe I don't need to. For this audience, you're just happy with solving SPDEs, and in some sense I am too. But the reason that I think it's important to pursue this type of thing is that we really do want to study spatially extended systems with noise. I'm thinking about climate modeling, hurricanes hitting the US coast, that sort of thing. So you've got some large system, and you've got some clearly defined coherent structure, like a hurricane or a vortex and superconductors or something like that. You want to know how they move. You want to know how many of them there are, what do they do. You want to be able to do statistics on them, and you want to be able to do numerics on them, but with some confidence. Okay, so the idea from the transfer integral of having quantities that you can that are exact, that you can compare your numerics to, is pretty attractive. Okay, but anyway, some questions, and a first principles theory of nucleation is still pretty difficult. Okay, also we started off at the beginning looking at the SPDE second order in time. So you've got this damping parameter, and the equation that I've been showing so far is what happens when the damping is large, tends to infinity. Okay, but it's interesting that the dynamics of individual kinks, if you study this equation with some small or intermediate value of eta, looks very different. Kink motion is ballistic. They can bounce off each other. They don't always kill each other. However, it's interesting that the stationary density is exactly the same. Okay, so you've got a very different type of dynamics that's producing the same stationary density, in particular the same mean number of kinks per unit length, same mean square at a point, same correlation function, and so on. It's quite fascinating that a very different temporal structure can give you the same average spatial structure. Okay, and of course, again, we thought that we'd study one dimension for a couple of months and then move on to 2 dimensions, and many years later I'm still talking about 1 dimension, but of course more than one space dimension is pretty interesting. Okay, that'll do.
Questions?
So did you say that these kinks follow Brownian motion?
Yeah.
But the lines look very straight in your simulation.
You think so?
Yeah.
Okay. No, I mean, you can measure mean of x squared versus time. I suppose I'm just using a long domain, so that the distance that they move in those pictures are not very large, but it's pretty clearly, yeah, Brownian.
I mean,
The
So
Brownian what, sorry?
Brownian web.
Web, okay.
Which the differentials and these transits show turning this into some kind of field.
I hope so. So which picture is described by the Brownian web? You mean the SPDEs?
The kinks that get created.
Okay. So you mean point particles in one space dimension? Okay. Yeah, so you can prove, or I suppose to an applied mathematician, you can calculate things, lots of things exactly for that model when you've actually got point particles. The picture always gets a little bit more muddy when you're dealing with the actual SPDE, where your kink has some width and you know, exactly, yeah. Brownian web, okay. Sorry? Okay.
In the coalescent environment.
Right.
No creation in pairs.
Uh-huh.
Maybe.
Yes, there is one.
Not in Chuck Newton's book.
Difference of opinion in the audience is fine.
No, actually, yeah, there are quite a lot of nice results on that system. Most of them are for the case without nucleation. That's right. But you can do quite a lot even with nucleation as long as you've got point particles in one dimension.
No more questions? All right, great. Let's think back.
Okay.
Very nice talk.